Okay, welcome to Module 6. And we're going to be talking about substations here and substation equipment. Okay, we're now at a point where you kind of understand some of the theory and the concepts and those things. Now we're going to talk about equipment and operations of equipment. So it should be a little easier to grasp and those types of things. Okay, that picture that you're looking at here is a substation in northern Reno. That's a 345 to 120 kV transformer right there in the center. And we'll be talking about transformers and circuit breakers and a lot of other things. Okay, so the objectives for this module are discuss the major high voltage equipment found in substations, discuss overhead and underground transmission and distribution substations, explain how high voltage equipment is protected from lightning, discuss the equipment found inside control buildings, discuss the main causes for high voltage equipment failures, and boom, we start with the first one. Here's substations. This is an overview of a substation in northern Nevada, and it is basically what we're looking at here is a 345 kV transmission line. This is a 345 kV gas breaker, sulfur hexafluoride, SF6 gas breaker. And that's driving the 345 to 120 transformer. This is a 120 kV bus or substation here. It's all the 120. Those are oil circuit breakers. The control building in the back, chain link fence. There's a ground grid under all of this gravel. And the fence is all tied to the ground grid. We have all those structures with little ground wire going to the ground grid. So everything is grounded. All the metal equipment is grounded. And then on these structures, these steel structures that are grounded, up above is the bus work, the aluminum tubing. Those are the three phases, and they're all aluminum. You don't get red, blue, green here in the real world. They're all aluminum. And they're either numbered 1, 2, 3 or ABC, sometimes colored with some tape. But the idea is it's three-phase, and we'll talk about all the different types of equipment here in the substation, starting with a transformer. We talked about transformers already in the AC module. Here we have a turns ratio. It's 2 to 1. Power in equals power out, just like before. So the voltage in times the current in is equal to the voltage out times the current out. Okay? And here's a picture of a transformer. Now, when you look at this transformer, there's a few things to note. This is the transformer itself, okay? That's where the coils and the windings are inside. Up above are the bushings that connect the high voltage wires to the coils inside. We'll talk about bushings in a second here. Then there's the low voltage bushings, and the lightning arresters are over here. Lightning arresters on this side, no, you can't see it too well here, but there's lightning arresters on the high voltage side and on the low voltage side. This berm here, in case any of the oil inside the transformer were to leak, it would be contained. And the oil in a transformer, when the transformer gets hot from all the power flowing through it, the resistive losses in the wires, transformer gets hot, the oil inside gets hot, and the hot oil rises. So the hot oil rises to the top, goes through the pipes over here, and goes into these radiators where the water, or the oil is falling and being cooled by the air. That's convection cooling, and the oil goes back into the bottom of the transformer. And then over here you have fans that help cool the oil as it's falling. Now this tank up on top is called the conservator tank. Now you fill the transformer all the way up with oil, all the radiators all the way up, and you fill that up to about halfway. So when the transformer expands and contracts in cold and hot weather and loaded and unloaded conditions, the oil level in the conservator goes up and down, and that's how you keep the transformer filled with oil. Now the oil serves two purposes. One, it allows for cooling, because we can take the hot oil out, cool it, and bring it in. So we can put more power through the transformer if we can keep the oil cooled and keep it cool. The other purpose for the oil is dielectric improvements. The dielectric strength of oil is much better than air. In other words, if our transformer were air, in the open air, you would have, you'd have to have the spacing of all the wires and everything far apart because air isn't as good as an insulating dielectric as oil. When you put oil in it, you can bring everything closer together because oil is a good insulator if it's clean and no gas in it. So basically speaking, the dielectric strength of air is about 100 kV per foot. What that means is if I had 100,000 volts on my fingers and I brought it together, closer together, I get to about a foot and I'll get an arc. Zzz. The dielectric strength of air is about 100 kV per foot. Now if you put those probes into oil, the mineral oil that's used in transformer, high voltage equipment, the dielectric strength increases from 100 kV per foot, which is roughly 9 kV per inch, to 30 kV per centimeter. So it's a huge increase, as long as there's no gas in the oil. Gas comes from arcing and sparking and insulation, burning and stuff. You get gases in the oil. That lowers the dielectric strength. So you have to do dissolved gas analysis to make sure your oil is clean, and that's part of a maintenance program that would go on with transformers. But still, the transformer oil is for dielectric strength and for cooling. And I want you to notice too, remember on the low voltage side of a transformer is high current. Notice how many conductors are on the low voltage bushing. There are 3 conductors per phase on the low voltage, yet on the high voltage there's only 1 conductor per phase because it's high voltage, low current. So you only need 1 conductor. And it's low voltage, high current, you need 3 conductors to handle that much current. So that's what happens in a transformer. Just the basics, you know, fundamentals of a transformer. There's a lot more to learn about them, ratings and emergency ratings and things like that. But here we have inside the transformer, we have coils like this. This happens to be, you can see the solid conductor here. That is a common, that'd be for a common Y or a neutral. You know, we have a grounded Y, so each phase, and then the neutral. And then we have the high voltage windings inside with their wire, they're going up to their own bushings. So this is basically inside a transformer we have all these windings. The windings are spaced with little spacers. And when there's a fault, they like to stretch like a spring. And if you fault the transformer too much, you lose some of those spacers and they fall out on the bottom and you don't even know it, and you can have a transformer failure the next time because of windings move a lot. Now here this drawing is showing some of the different ratios. Okay, we talked about the primary ones being the voltage ratio and the current ratios. Here's a bushing. Now this particular bushing, this is a close-up. I want you to notice there's an oil level in here that kind of lets you know that there's oil in the bushing. Now remember, oil is an insulator, and if you lose the oil in a bushing, you could easily destroy a bushing, and it could blow up. It could be shrapnel type glass, you know, porcelain blowing up all around. Here's the full bushing here. This part would be inside the transformer or circuit breaker. Notice the skirts or the ribs, or the different terms for the bushing here. What's happening there, the reason for all that is when you're exposed to the outside environment, the contaminants can get on there and collect on there, and then if you get moisture or condensation, the contaminants could be conductive, and the moisture makes a conductive path between the high voltage lead and the grounded tank. So you could have leakage currents, and if you get a lot of leakage currents, then you can get arcing underneath here, dry band arcing. If it arcs, then you're cutting out, you're making the leakage currents greater because you've reduced its path distance. So the skirts here are to reduce the leakage current in order to avoid scintillation activity and even a line to ground fault. Whereas inside the transformer or circuit breaker, you don't have exposure to the outside, so you don't need all the skirts and the ribs and that type of stuff, you know, to make leakage paths longer. Okay, those are bushings. Now, transformers have different oil ratings or different power ratings. When you don't have the fans turned on and you're just using convection cooling, that would be considered the self-cooling of a transformer. And let's say this one happens to be a 150 MVA self-cooled. When you turn on the fans, you might get an extra 25% more power through before the temperature rises above its rating. Normally, a transformer's temperature rises to 60 degrees at full load. You don't want to go higher than that. So if it starts getting higher, turn on the fans to keep it at 60. But now you get to load it up more, keeping it still at 60. And then if you have forced circulation, like oil pumps, as some of these radiators have, you can turn on the pump. Now you're pumping oil and blowing fans. You get forced air cooling. You might be able to go 2 times the rating and still keep it under 60 degrees Fahrenheit. So that's kind of what you're looking at. So when you're looking at a System 1 line and you see a transformer going up to 100%, you got to know, is that 100% of its full rating, or is it just air cooled, and yet you can go higher than that because you have other fans and things that can kick on? You need to know those types of things when you're operating a power system and trying to understand the operation of a transformer. Okay. Many different types of transformers. There's generation step up, there's transmission and subtransmission transformers, distribution, overhead, underground, instrument transformers, which are PTs and CTs, which we'll talk about in a few minutes, regulating transformers, phase shifting transformers, single phase and 3-phase transformer banks. I mean, transformers is all over the place. They're just part of the system. Just as many transmission lines, you got transformers. I mean, just a major part of the system. Okay, let's talk about regulators. In the case of regulators, what we're trying to do here is take a regulator. Here's a transformer that's taking like 69 kV down to 12.5 kV. So it's a distribution substation. Here's a regulator. This is a 3-phase voltage regulator. And what it does is it takes the secondary voltage and controls it plus or minus 10%. Then all of the circuit breakers and all the feeders, all the distribution lines off of that regulator are all controlled by that source voltage. So remember we were talking about the 60-to-1 turns ratio service transformer running that house that had the toaster? Okay. Well, that transformer is a fixed tap, 60-to-1. That means it has to be 7,200 volts or you're not going to get 120. And when you start loading up the distribution system, that 120 might drop to 118, 117. When it gets 116, we're getting pretty low, okay? And we're not going to get 120. We're getting 116. That means the 7,200 is not 7,200. It's low because we have a lot of load on the line. The regulator controls the primary 7,200 volts up and down based on the load of the whole distribution system that it's serving. So the goal is this. In most states, most jurisdictions, the power company is to provide 120 volts service plus or minus 5%. So 5% of 120 is 6 volts. So the highest voltage a power company can give, usually the first customer out of a substation, is 126 volts. The lowest voltage that the power company can give a customer, usually at the far end of a long distribution line, is 120 minus 6, or 114. Now 114 is on the low side. I mean, like I said earlier, don't call it 110. 114 is extremely low. So don't even think of calling it 110. But what we try to do is maybe add capacitors or watch conductor size and those types of things so we don't drop down to below about 116. Try to keep it above 116 and above. And on the high voltage side, not 126, 124, 125 maybe, 124, 123 is typically what you try to do as a first custom route. So the regulator is what's controlling the primary voltage, so all the 60-to-1 transformers out there can keep their customers within that band. So the regulator has settings and you can adjust it to regulate the primary voltage on the distribution. This is a three-phase regulator. You can also have single-phase regulators. It would take 3 of those. But a lot of utilities rather 3 individual regulators because a spare is cheaper. 3-phase regulators is cheaper than 3, but a spare is more expensive and more work. So trade-off, again, trade-off. Usually the regulators have bypass and disconnect switches for maintenance. It takes a lot of maintenance. So you would disconnect, you would bypass, so you give unregulated voltage, and then disconnect the regulator for maintenance. And here's basically how the regulator works. You have a common bushing, which is typically the neutral. You have a source and a load. Okay? So when you put power from the transformer here, we now either increase the turns ratio or decrease, depending on how this is set up. If this switch here went to the A position, then you're adding turns and you're raising the voltage. If this were in the B, then the magnetic fields cancel out instead of add, and you're actually lowering the voltage. And with a regulator, what's very important to know is that the load bushing actually has 2 connections. It actually has to make before break so that you don't get arcing. So when you want to raise the tap, this connector goes to here. Now the load is connected to 2 taps, raising the voltage, and then if you have to go higher, this one goes up to there. But there's always a connection. As long as there's always a connection, you minimize the arcing. If you don't minimize the arcing, you get gas and oil. If you get gas and oil, the dielectric strength goes down and you have a regulator failure. So you got to clean the oil, get the gas out, and you have this type of a operation. Normally, you have 8 rays, okay, and each one has a half position, so you basically get 16 positions raising, 16 positions lowering, plus neutral is 33 positions to go plus or minus 10%. And that boils down to about 45 volts per tap change on the primary, which results in about 0.8 volts per tap change on the secondary. Like the 120 would go to 120.8 if the regulator changed to tap. Roughly how that works. So in the 3-phase regulator, you have this shaft that's turning, and here's your tap positions onto the windings all the way around. And as this goes around, you have, these are fixed taps going to the each of the windings, and then you're going to make between both these connectors are on this piece, and then if it's moved, one connector's here, one connector's here, and then if it moves again, both connectors are here, and then one connector here, and then here. You can see how it kind of goes around. And there's all 3 of them lined up inside a regulator, just to give you an idea. So what are voltage regulators used for? To regulate the distribution voltage so that services stay within 120 volts plus or minus 10%. Okay, here's what a gauge looks like on a regulator. Here you go, plus 16, minus 16 with neutral in the center. Okay, this is a load tap changer because it makes before breaks. This is a no load tap changer. It means no load. De-energize a transformer if you're going to change one of these taps. And these are usually taps on the primary, the high voltage winding. It's like saying if I have a 20-to-1 turns ratio, this might be 21-to-1 or 22-to-1. Give you a little variation in the actual turns ratio. So if your system voltages need to be changed or matched or whatever, you de-energize a transformer, change this, and then re-energize and connect everything back up, and it kind of gives you a little step up in voltage. It helps center the regulator, so maybe the regulator is way off on one end all the time. Changing the main tap, now it might be centered better. Those are no load tap changers. So in this picture you have a regulator. There's the gauge. This gauge right here is right down here so you can see what it is. And then there's a transformer and a regulator. When they're both together, transformer and a regulator, they're called a load tap changing transformer, or LTC. And you'll see a lot of LTC transformers in substations. A couple things about that. to do maintenance on the regulator, you got to take the whole thing out of service, the whole LTC. So you have to have a substation that has 2 of them, or be able to take the load off and put on another transformer somewhere so you can de-energize that transformer and still have load or service to the other people. So, you know, they're advantageous that you have 1 unit instead of 2, but maintenance still required, so you have to have at least 2 of those, you know, to make it really economical. Okay, the next area we're going to talk about are instrument transformers. I mentioned CTs and PTs. CTs are current transformers. PTs are potential transformers. In this case, we're going to talk about current transformers, CTs. And they're basically a coil, somewhat like a donut slipping over the bushing. The coil of wire picks up the magnetic field from the real current flowing through the main power line. And based on the strength of that magnetic field of the main current, tells us how much current is flowing in the main line. And since it's a CT, we have a turns ratio that says, depending on how you set that up, you can have 1,000 to 5. That means if there's 1,000 amps going through the main conductor, you get 5 in the CT circuit. So if you can set it for 800 to 5, 600 to 5, you know, 400 to 5. So essentially, you could take 5 amps and work with protective relays, system control SCADA, or metering, or any telecommunications. It's a much lower current to deal with. It's a lot safer, it's a lot easier. It's a scaled down quantity, but you know it's whatever current is on the secondary, it's that turns ratio on the high side. So you know what the high current is without having to measure it exactly. You've got a ratio of it. Okay, that's a CT. Sometimes you have to have a standalone CT where current goes through the top here and you're just measuring the magnetic field and bringing that into the substation. That's a 230 kV freestanding, actually that's a 500 kV freestanding CT. This is a donut CT. Smaller ones are used in metering. If you were an industrial customer and you had a small CT so that you can, your meter that's on the side of the building is operating on a much lower current than the real current that's flowing through the power line. Here are PTs. There are 3 PTs here, 1 for each phase. This is an older type wire wound, and this is a phase-to-phase PT. And single phase PTs line to ground measure bus voltage. So when you're in System Control Center and you're looking at a one-line diagram and it says bus voltage is 236 kV, where does that information come from? It comes from a PT like this out in the substation that's actually measuring the voltage, dropping it down to something like 120 volts, so there's a turns ratio. That goes into a transducer, which further reduces that ratio down to something a computer can recognize. And then that information is sent to System Control, and System Control computer multiplies those 2 scale factors and gives you the real number back on the screen. So when you're looking at that number on the screen, picture coming from the actual substation PT or CT. Okay? So that information is really coming from the real world, scaled down through PTs, CTs, transducers, communicated as binary numbers back to the System Control Center through communication circuits, which we'll talk about later, and then converted back to real numbers and displayed on the screen. You're going to see the same thing on the simulator. You're going to see bus voltages. You're going to see bus voltages collapse. That's what the PTs are telling you. Hey, you're doing something wrong, or you better fix this quick. Okay. Now, talking a little bit about circuit breakers, these 2 breakers here are SF6 gas breakers, sulfur hexafluoride. It's an inert gas, it's a safe gas, it's extremely high dielectric strength, much, much better than oil, but it doesn't have any cooling properties, so you can't use it in transformers really. I mean, there's some transformers out there, but they're getting cooling a different way. But this is a live tank versus a dead tank. Let's talk about the dead tank first. The dead tank, the circuit breaker contacts. You know, a circuit breaker is really designed so when the current is flowing through, you know, let's say through here, okay, I got contacts here. When I open up the contacts, there's going to be an arc, but it stops the current flow, turns off the lights, okay? That arc that's in there, the more current, the bigger the arc. If you have full load, you could have a tremendous arc, but if you have an arc, you could put oil in there, the arc is reduced. If you put SF6 gas, the arc is greatly reduced, okay? So depending what you have in there, you could have vacuum, you could have, you know, air is like an air switch. It's like hardly any dielectric strength, but vacuum helps. Oil is better, and SF6 gas is better yet. Okay, now, here there are two arcing connectors right there, the two connectors in series. Okay, it's a manhole plate that you can take the bolts off and inspect. So there's mechanisms here, so the current is going through here. Those are CTs. There are 3 CTs stacked on that bushing and 3 CTs on this one. So that's for protective relays and what have you. That's all the CTs, the donut CTs. Now, the current goes through here. You open the breaker, those contacts open, and current stops flowing. CTs will register 0 power or current flow. These are voltage gradient rings. Up here, it allows the electric field to be equal on all around, so it kind of makes it a little bit more symmetrical and less stressful in certain areas. It balances out the electric field. These dead tanks are all grounded. There's ground wires there to the ground grid. It's all ground. You could actually touch all that. Okay? In the live tank design, the contactors are up here. The SF6 gas is up here. Your current is going straight through up here. This down here is grounded, but there's mechanical mechanisms inside here that control the contacts up here. And then CTs, no donut CTs, but standalone CTs. This is all grounded. So that's live tank where the connectors are up there, and this is dead tank where you're surrounded in a vessel that's grounded. Okay, here's oil circuit breaker. Oil in here, filled with oil. What happens is you got a bushing that goes down here and a bushing from the other side. They're in a V because the dielectric strength in oil is better than air. In air, you got to keep them farther apart. In oil, you can keep them closer together. But down on the bottom, you have almost like a U shape. You have at the bottom of the bushings, okay, you have a U that goes up and makes a connection. That if you push it down, it breaks the connection. If you pull it up, it makes the connection. Okay, and that U control, that connector there, goes up through a rod, and the rod goes across the top, goes into this box, comes over here to this box, and right up in here there's a rod. You can barely see it, but there's a piston here. So if you take compressed air, there's a compressor, and compressed air, you can put air in the bottom and it pushes the piston up, which closes the breaker, or the other way around. Or you put air in the top, it pushes that piston down. So you can make that piston go up and down, which through leverage makes the breaker open and close in oil. So all the CTs are inside the unit, and all the wires are all on the side here inside the cabinet for connecting up the CTs to the protective relays and telecommunications and what have you. So that's an oil circuit breaker. Trying to move away from oil causes environmental issues. Those types of things are moving in toward much more towards the SF6 gas. Okay, another type of breaker is the vacuum breaker. Usually on distribution. They don't, not as good as oil or not as good as gas, but they definitely help. It's better than air. The arcing contactors are in vacuum. It helps. Then we talk about circuit reclosers on distribution lines. And what the difference here is they're kind of like circuit breakers, except for they have automatic reclosing features, and they have automatic protective relaying schemes inside them. So on distribution, here's a recloser here. It's really a circuit breaker with a reclosing feature. Now, 3-phase, the source side and the load side, a control box. Now this one has a lot of bird guards and squirrel guard covers on it, a lot of plastic and rubber over all of it so that there's no exposed wires for squirrels or birds to come in contact and have a, an outage. But the idea here is when there's a fault on a distribution line, the recloser senses it through the CTs that are internal. And if there's an increase in current beyond its set point, it'll trip an open circuit breaker. But it'll wait 5 seconds and automatically reclose and re-energize the circuit, which is great. When you have a lightning strike and it hits and all the lights go out, 5 seconds later all the lights come back on without blowing a fuse or sending a troubleman out to fix the problem. But if it's a permanent fault, car accident, tree branch, or something like that, it'll trip, it'll reclose, and it'll trip out again, and it'll wait 15 seconds typically, and reclose again. If the fault is still there, it'll trip out again. It'll wait 20, 25 seconds, reclose again. If the fault is still there, it'll trip out and lock out. Now, a couple things about that that you need to know on distribution. Number one is if you ever see a car accident or something that involves power lines, don't think that the power's out because the arcing stops, because it'll reclose, okay? And even a control operator will reclose it if a line goes out because they'll test it once. So you don't want to be there when the line comes hot again, okay? Number two, the first trip is a fast trip, sensitive trip, quick, immediate. And that's because it has to be faster than the fuses that are put out on a distribution line. So when a lightning strike hits, the recloser at the substation or on the line trips before a fuse melts. Then when it recloses, everybody's back in power because a lightning strike is just sudden and it's gone. But if there's a permanent fault, the first trip is fast, second, third, and fourth trip to lockout are usually on time delay to allow a fuse to melt. So the first trip, if a car accident happens, boom, it's fast trip, and then it recloses. When it recloses on a time delay, so it's going to burn in. The next fault is going to go before it finally trips. And then it's going to come back and reclose again on time delayed, thinking a fuse is going to melt. But a car accident might not be where there's a fuse. So you don't know if it's going to keep energizing until it finally isolates itself. And if there's fused laterals coming off the feeder, then just that lateral fuse will melt and just those customers are out of service. If it's a main feeder that this happens to, then the whole feeder goes out with the recloser. So it just depends. So I'm just saying there's reclosing and there is tripping. And you'll learn more about this in distribution courses that we offer. So this is basically the gist of a recloser on the distribution. Okay, now we're going to talk a little bit about disconnect switches. Disconnect switches are air brake, they're visible switches. They got a lot of them have these whipping horns on it or arcing horns and whips. And the idea there is when you're trying to open up a circuit and there's a little bit of load or line charging or something on there, when you've got this connector, when you open it up, there's going to be an arc. But if you have these little whips or these arcing horns or something, what happens is the main contact's open. Now you have high resistance steel, increasing the resistance, reducing the current flow, reducing the arc, and then finally it just kind of breaks apart because they're spring loaded. Some of those longer ones have a pretty good whipping action to help extinguish the arc. Here's a vertical disconnect here. This switch goes up. You turn the control mechanism, which is down here. You can kind of see it. But when you turn that, this goes up, and this is an arcing horn trying to smooth out that arc. It's a vertical disconnect switch. Now this disconnect switch here has vacuum bottles associated with it. So when this switch opens, the arc is actually opening in a vacuum bottle, which allows you to open up some current. Now these are gang operated, which means all three operate with the same control rod. All three switches on a common control rod operate all three at the same time. So timing is an issue. Sometimes one opens before the others, and that could be a problem. Then the rod that comes down could be hand cranked with a hand crank this way. It could be a lever this way. It could be a pull down, or it could be like in this other picture, motor operated and then controlled through system control. So you have motor operated, you have manual, different types of switches. Okay, now let's talk a little bit about lightning arresters. And the purpose of a lightning arrestor is to be the weakest link in the insulation chain on the system. In other words, we put our wires up and space them so that they can have a certain amount of dielectric strength. And then the first thing that should fail is the lightning arrestor. It actually, in the older ones, were gaps. There was an air gap in there. So when the voltage got high enough, the air gap would close and the lightning arrestor would put a dead short right on the line and trip the breaker. And that's usually what happens. A lot of that still happens, even with the newer arrestors. But the newer arrestors are metal oxide, zinc oxide. They're a semiconductor. So when the voltage gets higher, then the resistance starts to get lower. And then when the voltage gets too high, the resistance gets lower and current flows and actually limits the voltage, kind of like a clamping device. But if the voltage gets too high, it'll limit so hard it'll still trip a breaker. But the metal oxide can handle a lot more energy. All these arrestors, whether it's on distribution or transmission, operate the same way. Here on distribution, you actually have a pressure relief plug on the bottom. If that arrestor takes on too much energy because a slow circuit breaker is not tripping, the bottom blows out of these things. Okay, so you can kind of see it hanging there. That's a bad arrestor. But if you have good coordination, these arrestors can go hundreds of thousands of times and still be operating good. The higher voltage ones operate the same pressure release, and they still try to limit and clamp voltages. It's just higher voltage. And they're the ones that are supposed to operate first before a line burns down or the voltage gets so high on a transient from a lightning strike that it damages a transformer. That's why you'll see lightning arrestors on both sides of a transformer, common, just so to protect that expensive transformer. Okay, and talk a little bit about lightning in the United States here. This is what's referred to as an isochronic map. It has to do with the average number of lightning storm days a year. Florida, for example, has 100 lightning storm days a year versus the Pacific coast of California. Here's 10 down by San Diego, and that's even inland a bit. Up here in Washington and Oregon is 10. It takes a while before you even get to 20. But if you look at Texas, you got 50, and you get into some of these states here, 60 and 70. And Colorado's a high lightning area. So when there's a lot of lightning, companies do extra to protect from lightning strikes, like lightning arresters, static wires or shield wires on transmission lines, etc. This is another look at lightning. This happens to be flash density, how many lightning strikes, in a period of time, the lightning strikes per, square mile or what have you, and it just kind of gives you an idea of intensity, lightning intensity in different regions of the states. They have maps like this for Canada, for all over the world. Okay. This subject is now capacitor banks. Remember we talked about capacitor banks and AC fundamentals, and how it has leading current and what have you. And it said if we add capacitor banks to capacitors to inductive loads, you can zero out the power factor and get more efficient. Well, the bottom line is this: we naturally go to the stores and we buy for load. We buy resistive load. electric stoves, electric water heaters, heaters, lights, anything that's electric load. We buy a lot of resistive and inductive. When it comes to inductive load, we buy a lot of motors. If it's blenders or drills or mixers or refrigerators or washing machines, a lot of motors. But we don't buy capacitors. We don't buy capacitor loads. There really aren't many available. Maybe bug zappers might be one where you've got, two meshes of two screens separated by a dielectric, and if a bug gets in between them, you have resistive load for a moment there. But then it goes back to, a capacitor. But not everybody owns a bug zapper. I don't. But because of that, power companies have to install capacitor banks to offset all the motors we have out there, all the conveyor belts and everything else in the world, all the motors. So here's a capacitor bank on a distribution pole. You can see the capacitors here, one for each phase, and there are multiple units per phase. Here's a capacitor bank in a substation. There might be an industrial area that maybe from 8 to 5 you need to turn on the capacitors, okay, and just get that capacitor, on there to compensate for all the motor loads to reduce the current, improve the power factor, reduce the system losses, raise the voltage, all those reasons for capacitors. Okay? So that's substation and distribution capacitors. Opposite are reactors. Now, reactors are the term used for inductors. So you have capacitors and inductors, but in power systems they don't call inductors, they call them reactors. I don't know why, maybe because of reactants or something, but they're called reactors. This is a 345 kV reactor. All it is a coil of wire to ground, 3 of them, one for each phase. A transformer would have 2 sets of coils, so you can transform voltage up and down. This is just a reactor. It's just a coil to ground. It acts as an AC load. If there is a very long transmission line, the purpose of this particular one, a 200-mile 345 kV transmission line, when you energize that line at one end, the other end, because of the capacitive effects of a very long transmission line, the charging and the static charge and what have you, you actually end up with maybe 365, 375 kV instead of 345. So you have the reactor on when you energize that line. You're going to learn this if you're doing system control operator stuff. This is what the reactors are for. So when you energize that line with the reactors on, now you're at maybe 355. Then you can close the circuit breaker to the transformer, pick up load, and let the load hold the voltage down and turn off the reactor. Okay, so the reactors are used to lower the voltage, okay? So here's a 3-phase, 35 megavar shunt reactor, okay? Now, another purpose of the reactor is late at night, and you'll learn this, late at night you have very low load and very high transmission voltages. So you turn on the reactors to keep the transmission voltages down so that your distribution regulators don't have so far to lower the voltage. Then early in the morning when load starts to pick up, you turn off the transmission reactors. Okay, more load comes on, you get a lot of load on, now you turn on the capacitors. When you turn on the capacitors, because you have so much load on, now in the afternoon, the evening, the load starts to come off. You turn off the capacitors. The load is coming off more and more. You get late into the night. You turn on the reactors. So you're controlling transmission voltage with reactors and capacitors. And let the regulators handle the distribution fine-tuning. Okay, now, this is a picture of a static VAR compensator. This is a device, equipment that is used to house both reactors and capacitors. If you look here, we've got capacitors and we have reactors. And between the two, you can control the VAR flow on the transmission line. So it's actually controlling, it's compensating for the reactance and capacitance of a long transmission line to make the line electrically shorter, to be more stable, to improve system reliability and those types of things. A static VAR compensator is a combination of capacitors and inductors to help the electrical characteristics of the power system. Inside of a control building, you'll find the equipment associated with batteries and chargers and protective relays and CT and PT connections to the relays. It's air conditioning and heating, because you might find telecommunications equipment and computers and things of that nature that are sensitive to temperature extremes. You have the low voltage panels for lighting and battery chargers and that. So in the control building, you'll find where the sensitive equipment is, or the connections, or where all the metering and protective relay and telecommunication equipment reside. Here's a picture of a typical battery bank in a substation. This battery bank is used to power the relays and the telecommunications equipment, what have you, because that equipment cannot be on AC power, because if the AC power goes out, you can't control the equipment. When you have batteries, these are usually about 125 to 130 volt DC battery banks. When all the equipment, the protective relay, telecommunications, all the control center equipment is all operating on batteries, when the AC power goes out, you can still operate, you can still control things via the batteries. When the batteries go out, then you're dead in the water. You actually have to have somebody out at the station doing everything manually. So that's a battery bank here, typical. Battery chargers. Now, in underground distribution systems, in some of the very large cities, like the city of Los Angeles, Atlanta, Georgia, some of the larger cities, and not necessarily that large, you have underground networks, underground distribution networks. And these transformers are three-phase. You can see the three phases, and there's the neutral for the grounded Y. And they operate 120, 208. So it's 208 three-phase. We'll get into that later in the distribution side. But these networks actually parallel transformers, so that 208, 120 three-phase power that's throughout the city streets, when you're hooking up power to a building, you just tap onto that and there's your power. You tap on and go. You don't have a bunch of transformers all over the place. You just have this underground distribution network with all these transformers running in parallel, providing simultaneous power. And if there's a problem in there in the vault, it becomes very major. You have to trip all the transformers to stop it, or cut the cables or what have you to stop the arcing. Underground networks are designed for high reliability, so even if there is an arc, you still get good voltage at the other side of the city and things are still operating even though you have a big arc going on this side. So it's a different animal, and it's a whole subject on itself, talking about underground distribution networks. Here's another picture of an underground network. You can see the three primary voltage, the small wires here, the high voltage, and then you have the low voltage bus bar with a high current. Here's another picture with one of the breakers pulled out for maintenance. The high voltage wires here, the low voltage multiple conductors over here. Underground distribution networks. Here the wires, the conductors are close together. They're taped because of animals getting in there. Stop them from touching. Three phases, the neutral over here. In summary, on the substation module, we talked about high voltage major equipment found in substations. We discussed the overhead and underground transmission and distribution substations. We explained how high voltage equipment is protected from lightning. We discussed the equipment found inside control buildings. And we discussed the main causes of high voltage equipment failures. A couple of things I want to add to that one point, though, is that in transformers, for example, some of the causes could be, the gas and oil and causing low dielectric strength, and that could cause arcing, and that could cause a transformer to fail. The SF6 gas in circuit breakers becomes a liquid at minus 40 degrees. Now, if minus 40 degrees is Fahrenheit and Celsius, I mean, that's the one temperature that it's exactly the same temperature. And then you have problems like you can't open the breaker, you can't close the breaker, so you have to have, maybe heaters on the tank so that it keeps the gas warm or make sure the pressure, there's different issues there. Sometimes the timing on breakers, the three phases is not exact, so you've caused transients to occur. Sometimes you have bushing failures. If the dielectric oil fails in the bushing and the oil falls into the main tank, you end up with a failing bushing. There's a lot of problems that can happen in the substation. There might be contact. There might be somebody getting into a substation trying to cut neutral wires and what have you, and causing issues on ground faults and people that shouldn't be in substations. I mean, there's several causes. Birds could get into equipment, snakes. There's even maintenance on equipment. So there's a lot of different causes of high voltage equipment, but we do what we can to do preventative maintenance, but even then they're still vulnerable to some kind of action. So that's pretty much the conclusion of substations. Thank you.